Hello, in this video we're going to be looking at the trapezium rule, which is usually used when it's impossible to integrate a function, but we still want to work out what the area is underneath the curve. So as it says, if you cannot integrate a function algebraically, you can use a numerical method to approximate the area beneath the curve. For example, let's say we wanted to find an estimate for the area bounded by y equals f of x, the x-axis, and the lines x equals a and x equals b, as drawn in the diagram. So we could divide the area up into n trapezia, each with a height of h, although the heights are horizontal. And then if we call the y values y0, y1, y2, all the way up to yn, then these will represent the parallel sides of the trapezia. So the first trapezium would have a height of h and parallel sides of y0 and y1 as shown. The second trapezium would have the same height, h, and parallel sides y1 and y2. The third trapezium would have the same height but parallel sides of y2 and y3 and so on, with the final trapezium having a height of h and parallel sides yn-1 and yn. Now we know that the area of a trapezium is given by half the sum of the parallel sides times the height between them. So if we want to add up the area of each trapezium to find the total area under the curve, the area of the first trapezium is half of y0 plus y1h, the area of the second one is half of y1 plus y2h, and so on down to the area of the final trapezium being half of yn-1 plus ynh. So if we look at factorising all of that, we've got a half and an h in every area. We've got 1 y0 in the first trapezium, we've got 1 yn in the final trapezium, and then we've got 2 of everything else. We've got 2 y1s, 2 y2s, and so on. So there is our formula. Total area equals half of h multiplied by y0 plus 2 of all the other ones apart from yn. So this is what the formula looks like for the trapezium rule in the formula booklet. The integral of a to b of y dx is roughly equal to half h, open brackets, y0 plus 2, y1 plus y2, all the way up to yn-1 plus 1 yn, where h is b minus a over n, i.e. an nth of the gap between a and b. We're going to look at two examples. For example 1, the figure shows the graph of f of x equals 12 minus the square root of e to the 0.4x plus 2. We've been asked to use the trapezium rule with 4 trapezia to find an approximate value for the area enclosed by the curve y equals f of x, the axes, and the line x equals 12. So since we've been asked to use 4 trapezia, each one will have a height of 3. Since we're going between x is 0 and x is 12, and 12 minus 0 divided by 4 using the formula is 3. And as you can see, I've taken the liberty of actually drawing the 4 trapezia and colouring them in different colours. And as you can probably appreciate, our approximate answer for the area will be an underestimate of the actual area because there are gaps above our trapezia between the trapezia and the curve. So we have 5 y values. There's always one more y value than there are trapezia. I've labelled them y0, y1, y2, y3 and y4 on the graph. And then we need to substitute the x values for each of those, 0, 3, 6, 9 and 12 into the equation f of x equals 12 minus the square root of e to 0.4x plus 2 to find the values of y, because they are the parallel sides we need. So I've done that. I've written each of the values of y to 2 decimal places, and then substituting the numbers into the formula. We always start with a half. H is 3. The height of each of the trapezia was 3. We've got one lot of 10.27. We've got one lot of 0.89 at the other end, and then we've got 2 lots of everything else in the middle, 9.69 plus 8.39 plus 5.79. And when we evaluate the answer, we get 88.35. Again, that's to 2 decimal places. Now, for example 2, we've been asked to find an estimate for the area under the curve tan of a third of x between pi over 2 and pi. And it turns out that actually we can integrate that, which we're going to be doing in part B, and then comparing the percentage difference between our approximate answer and the actual value in part C. Anyway, focusing on part A, find an estimate for the integral between pi over 2 and pi of tan x over 3 dx using 5 ordinates. That's 5 x values. That means 4 trapezia. Correct to 3 decimal places, finding all the y ordinates correct to 3 decimal places. Okay, part B, prove that the integral is actually 3 over 2 ln 3. And then part C, as I say, find the percentage difference between our approximate answer for part A and the actual value of 3 over 2 ln 3. It's always a nice idea to see what the graph looks like. So that's the graph of tan of a third x. We've been asked to use 5 ordinates, x values, which, as I say, is the same as using 4 trapezia, because there's always one fewer trapezium than the number of x values, number of ordinates. So each trapezium will have a height of pi over 8, because A is pi over 2, B is pi, the difference is pi over 2, and we divide by 4 because there are 4 trapezia. So h equals pi over 8. So given that we're using the trapezium rule between pi over 2 and pi, and that h is pi over 8, we can work out the x ordinates by adding pi over 8. So pi over 2 plus pi over 8 is 5 pi over 8. Then we get 6 pi over 8, which cancels to 3 pi over 4. Then 7 pi over 8, and finally pi. And we need to work out the y values that correspond to each of those x values. So here is a complete table, and you'll remember in the question it asks us to give the y values, the y ordinates, to 3 decimal places. So we've got 0.577, 0.767, 1.000, 1.303 and 1.732. And then using the formula, again, h is pi over 8. We want one lot of 0.577, one lot of 1.732, 2 lots of everything else, and we get an answer of 1.659. Again, that is written to 3 decimal places as requested. So for part B, we've been asked to prove that the integral is 3 over 2 ln 3. So the first thing to do is actually to integrate tan of a third x. And we know that the integral of tan x is log sec x. And by substitution, we can find that the integral of tan of a third x is 3 ln sec x over 3. Substituting pi into that is going to give us 3 ln sec of pi over 3, which is 3 ln 2. Substituting pi over 2 into that gives us 3 ln sec pi over 6, which is 3 ln 2 root 3 over 3, or ln of 2 over root 3. And then by dividing, you've got 3 ln of 2 over 2 root 3 over 3, which gives us 3 ln root 3, or 3 ln of 3 to the half, and then bringing the half down as a coefficient gives us 3 over 2 ln 3. And then to find the percentage difference, we want to find the difference between the actual value and the approximation and compare that with the actual value by dividing by it and then timesing by 100. It doesn't matter which one is bigger, the actual approximation, because we're going to find the magnitude. So substituting numbers into the formula, we get 0.67%.